Hello, welcome to the third topic of the course, and that is potential and congestion games. So these are two classes of games which we will see actually are isomorphic. Now let's, as you can see here in the illustration, and also in general, potential games, they are in a way a physical way to look at games where the players have a common goal. That is something which we will formalize by saying that they have a potential. So they want to optimize something which is common. For example, when the players play in the same team, when you cooperate with your colleague, when you cooperate with other people in economics, most people have actually common goals. Yes, when there is someone who sells and the other person buys, then they actually have an opposite interest as to the price. Of course, the seller would like the price to be as high as possible, while the buyer would like to pay as little as possible. But in general, most situations, or at least many situations, have a lot of common goals, and that's in a way opposite to the other class of games we are going to study, which is called constant sum games, and that is basically when people have opposite interests. So when the sum of what they get is constant, so if I get more, the other person gets less. Now, that's also sometimes the case. Like, for example, in rivalry games, so competitions like in a war. So even in a war, you don't have only constant sum, because sometimes you would just like to prevent people from being killed from both sides. You prefer to achieve something which is opposite to what the other person tries to achieve, but like humanitarian goals can actually be aligned still. But the constant sum games, they actually are often or mostly taught on such introductory courses. Now, the in a way opposite, but also important, of course, topic of potential games, which we are going to study now, is usually not taught on such introductory courses. And actually, it's not presented in the books, it's actually presented in the paper I've mentioned. You don't have to read the paper, of course, but you can if you would like to get it better. Now, I've chosen to teach that part on the course, because I think that that's logically very similar to zero-sum games. Yeah, historically, zero-sum games were more important, and they were the first to be studied and all that. But logically, both subclasses are very important. In a way, they play similar roles. So potential games are about aligned interest. Zero-sum games are the epiphany of opposite interests. So they are both important. So I think it's good that we study that. And no topic is extremely complicated. Well, there are some, let's say, cumbersome places where you have a lot of notation, but that's all. That's everything possible to understand. So, as I said, condition games turn to be another description of the same class, but we are going to first start with the potential games. And that's an idea which is common also to physics and to algorithm analysis. When you have something which represents a value of a point in space, which can be used to describe the energy of any body, any physical body, given the potential of space. For example, the gravitational or the electromagnetic potential. By analogy, in algorithm that was studied, used as a technique to analyze for example, the amortized complexity. When you look at again the one common function which represents how much time or something or some other resource the algorithm has used in total, or something which is a function of the state of the thing that the algorithm manipulates, And that's the analogy to the physical potential. We're also going to have this function which represents the utility of the players in general. That's the reason it's called potential. Of course, the physical and algorithmic potential, these are just something to remember that these are in a way analogous, but we don't study those. We study some other notion of potential, which I will shortly describe. And the notion of congestion games is, of course, also taken from applications. So we have many interactions when we at least can have congestion on the network, on the road, and so on. And here we are going to formalize that too. So these are also very important interactions. And so let us just briefly outline the plan. So having introduced the topics, we are going first to dive into the potential games and their properties, which are very, very cool, often in other studies in more advanced level than of course we have now. Still, it's important to know what happens for potential games. They often allow for a more for a stronger result, for better insights, and so on. So they have some properties, some of which we are going to cover today. First, we're going to define several variants of the potential games. There are many variants which are weaker, and then the strongest we're going to study are actually potential games. Now, then we're going to exemplify all kinds of variants. Well, the first conclusion is about the existence of Nash equilibria of such games, at least for finite games. And then the second conclusion is going to relate to the so-called improvement paths and finite improvement property, which is basically equivalent to a very weak notion of potential called generalized ordinal potential. Then we're going to look at some other definitions of potential, which again, of course, we are going to prove them here, but in a way they can be said to resemble some physical stuff related to paths, and that on any closed path you have some change which is zero. So they do resemble physics, the physical potential. And the final topic which relates to potential is the usage of potential to pick a concrete equilibrium in the case you have several Nash equilibria. So the potential function can be used to refine the notion of Nash equilibria, at least of Nash, maybe also of other equilibria. It depends on the equilibrium. Now the second big topic, which is as I said connected, is congestion games, which after we've defined them, we're going to exemplify, and then finally to show that they are isomorphic with potential games. Okay, so let us dive into the first topic for potential games. So when we get beyond the notation, you're going to see it's quite simple. So the first notion is the most general definition of a potential game, and that's called generalized ordinal potential. So when you have a game, a strategic form game, and you have a function from the set of strategies of all the strategy profiles to real is called the generalized ordinal potential. If it basically whenever the utility of some player who unilaterally deviates grows, the function also increases. Formally, for any player I, for any subprofile of strategies of the other players, and for any two strategies for that player I, we have the utility of player I changes. Let's see how it changes from being playing Si to playing Ti to playing Si when the others play S minus I. And then what we say is that if that utility has grown, if the change is positive, then also the change in the potential function between the profile when everyone plays S minus I and play I plays Si, and when everyone plays S minus I and play I plays Ti, that's exactly of the same sign. So if play I increases her utility from moving from Ti to Si, then so does Pi. So does P, the potential. So potential is a function which follows the utility change of any player who unilaterally changes the strategy. But it does it for all the players. And if there is such a potential function, such a game is called the generalized or ordinal potential game. So it's much more general, the restriction is much looser than on a general on just a potential game. It's generalized ordinal potential game. And please notice that we have chosen to define that thing. One can ask, why don't we define the other direction? We don't indeed, because this, what we have defined now, would imply that if the player can improve, then the potential grows. And since it cannot grow indefinitely when, for example, the game is finite, then at some point, no player can improve, and at some point, it's an equilibrium. So that definition, if it holds, will imply something important, imply the existence of an equilibrium for finite games. But the other direction, that there is a function such that if that function grows, the utility grows, it's not that interesting. What is interesting is that if the utility grows, then that's also accompanied by the growth of the function, so that if the utility could grow indefinitely, then the function will grow indefinitely, so that if the function cannot grow indefinitely, the utility cannot. So we're going to see that. I'm just saying that there is a reason that we define only that direction. But we also want to define something more general. So that was the generalized ordinal potential. Now we drop the generalized, and now we define just some thing which is called ordinal potential. So now it's going to be less general. It's going to be more restrictive in the requirement, stronger requirement. So given a game, a function from the set of strategies of all the game, to variance is an ordinal potential if for any player, for any strategy set of the profile of the others, and for any two strategies for that player I, the utility of player I increases from moving from Ti to Si, given that the others plays minus I, if and only if the potential increases when player I moves from Ti to Si, given that the others plays minus I. So basically, the potential function exactly the sign change is equivalent to the sign change in the utility, and that's about the order. So whether utility grows or not, that's why it's called ordinal potential. So the magnitude of the change can differ, but the sign is the same. So that's ordinal potential, but nothing is required for the magnitude of the change, ui in SIS minus I minus ui in TIS minus I, and the magnitude of the change in potential. So if there is such an ordinal potential, the game is called an ordinal potential game. Now, intuition is that, as I said, the sign of the utility change of the change in player, of the player who changes the strategy, is equivalent to the sign of the potential change on those strategy profiles. So there is a common indicator of the cost of the change, but only of whether it's positive or negative, or non-negative. Well, we can just invert it, and so the utility change is positive if and only if the potential change is positive, and that's equivalent to saying that the utility change is non-negative if and only if the potential change is non-negative, and so on. Now, so we have a common for all the players indicator of whether the change is positive or negative. Not actually of the cost itself, but of the direction of the change of the cost. Now, still a more stronger and narrower definition. Now we require something else. Now, given a game, a function is called the weighted potential if there is a vector of n weight, one positive weight for each player, such that for any player I, any strategy set of the other players, and any strategy T and S, Ti and Si for the player, the utility of that player changes when it moves from Ti to Si, given that the other players minus I, exactly to the extent that the potential changes times the weight. So basically, yeah, not only the order, but actually the magnitude is preserved up to those multiplies the weight. So it of course implies ordinal potential. And again, the intuition here is that they have basically the same cost of change up to these factors, the same cost represented by this potential function. Actually, an important thing to note is I've now changed the notation of the r plus to the n, so the n vector of positive integers to r plus plus to the n, to emphasize that these integers are strictly positive. Otherwise, we could have asked, what if you multiply the potential by 0? If the sign of this strictly always preserved, so the weights are strictly positive. You can divide by them. Okay, so we've defined the notion of weighted potential. Now we're going further and we're going to define an even stricter for this lecture, the final, the most strict, and the probably most common notion of exact potential or just potential. So a weighted potential with weights all being 1 is called exact potential. So basically, the condition now becomes that the utility change is exactly equal to the potential change. So the potential function exactly traces the changes in the utility of the unilateral deviator. Please notice the changes in the potential function are equal to the changes in the utility. So the function is not equal to the utility. In particular, the function can be always changed by any constant. The changes in the function, in the potential function, are equal to the changes in the utility. And we are talking about concrete changes when we look at the utility of, we are looking at the utility of the only deviator, the rest being constant. So what can one player get by deviating? That's a bit related, the logic is related to Nash equilibria. So what can one player get by deviating? That's a very important topic, but it's an interesting question. But there are many other questions you could ask. It's important to notice that what we have defined is exactly that. So that's important. And as we didn't hear, the intuition is of course common concept change. So let's now go back and see how backwards how we can be said to loosen our definition. So we actually have been making them stricter and stricter, but how we can be said to loosen them if we go backwards. So the potential is a function which is exactly equal it's the difference in the function, excuse me, are equal to the difference in the utility of the unique deviator. Only when there is a unique deviator, only then does this condition hold. We don't require anything else. Now, losing that can be done by allowing to multiply by the weight. Going back one slide, 2 slides, losing that in the further can be done by only requiring that the direction, the sign, I mean, of the change will be traced by the potential, and losing that in the further. So we generalize even the ordinal potential by only requiring that the change in the utility implies the change in the potential, but not necessarily the other way around. So this is the sequence of definitions, and the most useful definition is probably potential, but it's good to know all of them. And let us now see some examples that will show that the definitions don't define the empty set, and that there is a difference between all those definitions. In general, again, can be one, not the other one. So now let us exemplify why these definitions are important and nice. So, first of all, each kind of potential may exist or not exist. We have not defined something like which always exists or always doesn't. For example, the famous example we have already seen several times, matching tennis. So the strategies of 2 players, by the way, I have not defined it for only 2 players, but the example is for only for 2 players. This is A or B, and if the strategies match, then the row player gets 1 and the column player gets 0. And if the strategies don't match, then the row player gets 0 and the column player gets 1. Now, there is here no only that there is no potential, not only there is no weight potential, not only there is no ordinal potential, there is even no generalized ordinal potential. So by the contrapositive, that the exact potential implies it's a weighted potential, implies ordinal, implies generalized ordinal. The contrapositive says that if there is no generalized ordinal, the contrapositive, that's a logical notion. So if there is no what is implied, then definitely there is no what implies. So there is no ordinal, and if there is no ordinal, there is no weighted, and if there is no weighted, there is no exact. Now, why there is no general ordinal potential? Now, the cycle, look at the cycle of strategies. When exactly one player changes the strategy. So we are in the realm of those conditions. So from AA, we go to AB, so the second player changes the strategy. Then the first player, we go to BB. And then BA, the second player. And then we go back to AA by the first player changing the strategy. Now, if there had been a generalized ordinal potential function, then this function should have increased, strictly increased at every step. Yeah, because the change in player strictly increases her utility always. From AA to AB, the second player who changes increases from 0 to 1. Here, from AB to BB, the first player, I mean the row player, changes increases from 0 to 1. The second player actually decreases, but it does not matter. And so on. From BB to BA, the change in player, the column player, increases from 0 to 1. From BA to AA, the change in player, the row player, increases from 0 to 1. And here we are in AA, in the same place, and it cannot be that the potential function has been strictly increasing so that its value in an A is strictly smaller than its value in an A. So it cannot be that there is no generalized or ordinal potential function. such a circle in the set of characteristic profiles is not possible. I mean, it's not possible if there exists a non-generalized or a generalized ordinal potential function. So the mentioned penis, it does not have a Nash equilibrium, I remind you. I mean, pure Nash equilibrium, it does not have, and it does not also have a generalized ordinal potential. It does not have either of them. We are going to soon see why it's related. Now, another example. A game which does have the generalized ordinal potential, but does not have the ordinal potential. So the game is generalized ordinal, but it's not ordinal. The same way as we could say that matching penis, going back, is not a generalized ordinal game or a generalized ordinal potential game because it does not admit a generalized ordinal potential function. This game we are now introducing without even calling it some way is a example is a generalized ordinal, but it's a generalized ordinal, but it's not an ordinal. Now, why? First of all, there exists a generalized ordinal potential. Because this is, for example, a generalized ordinal potential. You can check that every time that there is only one player who deviates, and her utility strictly increases, the value of this function defined by this table also strictly increases. For example, when player 1 changes from A when they play C, and it changes to B when they play and now start playing BC, then her utility increases from 1 to 2, right? Now if you look at the function we suggested, it also increases from AC to BC. So its value on AC is strictly smaller than its value on BC. Now you can check that all this exists. It always fulfills this condition that when the utility of the only deviator increases, then also the potential increases. But there is no ordinal potential because if it existed, then look at the following path in the strategy set: AC to BC. So the utility increases and ordinal potential, even in the generalized ordinal, should increase. That should increase. Now, let us go to the profile BD. So, yes. So the only change in play is the column player, and the utility increases from 0 to 1. And the potential, or even ordinal potential, also should increase from BC to BD. Then, let's see what if we go to AD. So the role player already again changes. The utility increases from 0 to 2. The potential, or even the ordinal potential, or even the generalized ordinal potential should also increase. Now, we're going to use that we assume now that it's an ordinal potential, not only a generalized ordinal. And we're going to arrive at a contradiction. If further change from AD to AC, the change in player, the column player, maintains the same equality. Now, if it's a potential, then her utility has to also, the potential has to be the same. Right? Let us go to the definition of potential, ordinal potential. Now, increase if and only if increase. Change in the order, you will have decrease if and only if decrease. And then not increase if and only if not increase. And change in the order, not decrease if and only if not decrease. And from those two, equality if and only if equality. So from this if and only if, we see that equality is equivalent to equality. However, in the case of a general ordinal potential, this does not have to happen. It can be that the utility does not change, but the potential changes. So going back to the example, the generalized ordinal potential, when we go from AD to AC, we see it decreases. And it's okay for a generalized ordinal potential. But an ordinal potential has to exactly follow the sign change of the utility. It has to stay exactly the same because the utility does not change from zero. It goes from 0 to 0, the utility of the changing player. So then potential, an ordinal potential has to be the same. And we all have a right at a contradiction. So if there had been an ordinal potential, then its value on AC should have been smaller than its value on AC, which is of course not possible because it's a function. It can have only exactly one value on any strategy profile. So here it's a generalized ordinal potential game, but it's not an ordinal potential game. Now, a game which is even closer to a potential game. It is actually now an example of an ordinal game, so it admits an ordinal potential, but it's not a weighted potential game. Why? Okay. And of course, when I say it's not weighted, it immediately implies it's definitely not exact. Because exact implies weighted and so on. Now, one of among the infinitely many ordinal potentials, and we can check it's an ordinal potential, is this depicted here. Let's check just that it's an ordinal potential. So let's say that we move from AD to BD. So the only change in play is the role player, and she decreases her utility. The potential also decreases from 5 to 2 when we move from AD to BD. However, any weighted potential would have already, again, made us arrive at a contradiction, because imagine you have some weighted potential with positive weights, W1, W2. Now, when we change, look at the circle, we always look at the circle. That's also something which may be reminiscent of the physical analogy. So what if we have a closed path, in this case a path in the space of the strategy profile? What if we move from AC to BC, AC to BC to BD to AD, and then back to AC? So first from A to B, the only changing player, the role player, her utility increases by 1. And at the time, the utility of the role player will change when we move from BD to AD, and her utility will increase by 3. And that should make the potential function, if you recall the definition, change by 1 plus 3 times 1 minus 1, over W1. Because the change in the potential times the value is equal to the change in the function. Therefore, the change in the function divided by the weight is equal to the change in the potential. But we are looking at other changes too. So what happens when the second player, the column player, changes from BC to BD? Okay. When that happens, then the utility of the column player strictly increases from 0 to 1. And the other change is when the player, because we look at this counterclockwise circle, when the second player changes from AD to AC, then the utility of the column player changes from 1 to 0. So in total, it's one time it grows from 0 to 1, so it grows by 1. Another time it grows from 1 to 0. It decreases by 1. So it's 1 minus 1, and that divided by the weight of the other player, second player. And that should be equal to 0. Because the potential function eventually is equal to itself. We have come back. That's why the total weight should be 0. And of course, this cannot happen because this summand is 0, because 1 minus 1 is 0. And never will we have that 1 plus 3 divided by something will be 0. So W is just a real number. It's not infinity. There is nothing like that here. Okay. So we have proven that though there is an ordinal potential, there is no weighted potential, and therefore so the order cannot be linear in a way, and therefore we have proven that the game is, according to our definition, an ordinal potential game, but it's not a weighted potential game, not a weighted potential game. Now, even stronger. Now there is a game here which will show is a weighted potential game, but it's not an exact game. So there is no exact potential. So the players are not equal in their influence on the potential. They need weight. Now, again, the example just shows that, okay, there is a weighted potential. For example, this is a weighted potential with a weight half and 1. Well, let's see. So when the players, let's say, change from AD to AC, we cannot pay attention, look at the change from AD to, say, BC, because here we will need 2 players to change. But in the definition, we only describe what we require from the change when exactly 1 player changes. So when the column player here changes from D to C and the row player plays A, the utility of the column player, it decreases because it changes from 5 to 0. It changes by minus 5. And the now weighted potential changes exactly by minus 5 times 1, the coefficients of the column player, what we want. Let's look at one change of the row player. So when the row player changes from AC to BC, then the change grants her utility increase from 1 to 2, 1. And what about the potential? The weighted potential? It's 2, from 0 to 2. And times half the weight of the player, it's exactly 1, as we need. However, there is no exact potential, because the exact potential should have fulfilled, if you already have looked at this circle, counterclockwise circle, that the total change in the exact potential, which should have been equal to the total change in the utility of the change in players. So let's go from AC to, or let's start here, why not? Okay, we start here in this notation, we start from AC. So the row player changes from A to B, and the utility increased by 1. It should be exactly the change in the potential if there had been a potential. The column player here changes from C to D, and the utility increased by 1. The row player changes from B to A, and the utility increased by 1. Finally, the column player changes from D to C, the utility decreases by 5, from 5 to 0, minus 5. And we have got to the same place. So if there had been a potential, the total change should have been 0. And of course, it's minus 3, so it's a contradiction. There is no possible potential here. And you might think, what if there is no potential gain? There are no potential gains, but of course there are some. It would be quite funny to define something which defines the empty set. So we can, but no, there are some. For example, let's look at the famous, very simple case, identical utility games. I spoke that potential actually expresses that the pairs have something common. It does not have to be that they have exactly the same utility, but in particular, when they have exactly the same utility functions, it's an example of a potential game. So consider a finite or not game where the utilities of the pairs simply are identically the same function. Then just take the potential function to be as the utility, the common utility, and then by definition that will be the potential function, because the players have the same ideas of what they want. So the changing player gets some change in her utility. By definition, that's also the change in the potential, because that's the common utility. We assume the utility is common. Usually the utility is not common, so it's not so trivial sometimes to find the potential, but in this case it's trivial. And of course, it's a potential, therefore it's a weighted potential, therefore it's an ordinal potential, therefore it's a generalized ordinal potential. So that direction is known. Another example of potential game, our old friend, the prisoner's dilemma. So I'm now writing it in a parametric form. So I require A is strictly greater than B, strictly greater than C, strictly greater than D, which is non-negative. So it's always better to defect than to cooperate, because C is better than D. So if the column player defects, for the row player, it's better to defect than to cooperate. And if the column player played C, it would still be the same, in the sense that A is better than B. So it would be still strictly better to defect than to cooperate, and it's symmetric, so it's the same for the other when we invert the rows. So it's a prisoner's dilemma in a general sense. And that's a potential for this game. So you can easily check yourself that it's a potential. How do you do that? You can stop the video and think how to do that. You just check for any change. Here you can just manually check all the changes. Where exactly one player changes a deviate, the change in per utility is equal to the change in the potential function. Okay, finally, we've got, after those definitions and examples, to the first interesting conclusion from what it means to be a potential game.